Welcome back to Physics 141 online. I'd like to proceed now talking about two additional quantities for rotational motion that have very close analogies to quantities that we already studied for linear motion. And the first one is torque. When we have a rotating object, there is a way that we can apply a force to a point on that object that will cause it to rotate. And it's not enough just to consider what the force is that's applied. We have to also consider along what direction the force is applied and at what point the force is applied. How far that point is away from the rotation axis makes a big difference. So, as we go into this discussion, we can describe this torque in several different ways. Imagine that we have a force F that's applied to a point on this unusually shaped object. We assume the rotation axis is perpendicular to the page running through the origin. So the point of application of the force, you might think of it as a peg or a screw that we've inserted into the object, and we've tied a string around it, and now we're exerting a force F in the upward direction. R is the distance of that point away from the rotation axis, and theta is the angle that the force vector makes with the radial direction, which is given by the vector that goes from the center out to where the point is located. So, the first way of writing down the torque, and this is probably the most common way in textbooks, is to define the torque given by the Greek letter tau as the force, the magnitude of the force F, times the perpendicular distance of that force, the perpendicular distance of the line of the force to the axis. And so what does that mean? Well, in this case, we would take the F vector, the force vector, and extend it in both directions, perhaps with a dotted line, and then we would look for the perpendicular distance from that line to the rotation axis. And it's pretty easy to see what that would be here. Here we extend the force direction downward with a dotted line, and it crosses the x-axis, and the perpendicular distance, which some books refer to as r perpendicular, is just this distance here. Well, the angle theta is also the upper angle in this right triangle, so that r perpendicular is equal to r sine of theta. You can convince yourself of that with some simple geometry. So the torque, using the force and this radial distance r, is given by F times r times the sine of theta. And so it's easy enough to write that down. There's another way that we could express this same quantity in terms of the tangential component of the force. You see that this force vector is neither along the radial direction nor is it along the tangential direction to the circular path that this point is going to make when it rotates. So we could take the force and break it down into a tangential component which is along the tangent to that circle. And the tangential component to that force will be Ft equals F times the sine of theta. And a little bit of inspection of the right triangle here that has F and Ft as sides of that triangle will show you that that's also the case. So we can either write the torque down as the force times the perpendicular distance to the axis, or we can write it as the tangential force times the distance to the axis. They both give the same answer. Just remember that in this equation, it's very important that this angle theta is the angle between the force vector and the r vector drawn when they are tail to tail. And you can see here that the r vector in my sketch is in the same direction as the r vector over here on the rotating object, which is why the angle theta is correct. Now, what we want to do is consider the torque in terms of this tangential component of the force. And what we've written down so far is just the torque that's exerted on that little piece of mass at the location where the force is applied. We would like to add up all of the torques on all of the pieces of mass that make up the object and come up with an expression for the total torque on the entire object. One of the nice things about studying rigid objects like this is that when they rotate, they all rotate together. They all have the same angular velocity omega, they all have the same angular acceleration alpha, and so this simplifies the way that we study them. So the torque that's on a little piece of mass, a mass element delta m sub I, is just the tangential force times that distance r. Now the tangential force, the force in the direction of motion, is given by the mass times the tangential acceleration. Remember that as an object goes through circular motion, there's always an acceleration towards the center. We call that the centripetal acceleration. But if the rotation speed is increasing, then there's also an acceleration in the tangential direction. And that acceleration describes the rate of increase of the rotational speed. So we've replaced this tangential force with delta m times a in the tangential direction. So this gives us the torque on that one little piece of mass. Now we're going to substitute for this tangential acceleration, and there's a quantity alpha, which is the angular acceleration, and we've already studied how the tangential or linear acceleration is related to the angular acceleration through the distance to the axis. So this point, whose tangential acceleration is a sub t, is at a distance r sub I from the axis. So a is r alpha. When we make that substitution, we find that the torque on this mass element is delta m times r squared times alpha. The reason that this is useful is the alpha is the same for all pieces of the object. So now when we want to add up all of these torques to get the net torque acting on the object, we can sum up all of these contributions of all of the mass elements, but the alpha comes outside the summation because it's the same for all the mass elements. I put an approximation here because carving this object up into little mass elements only gives an approximate result for the net torque. The result gets better and better if we make the mass elements smaller and smaller. And you're already familiar with this kind of phenomenon in your study of calculus. So if we want to make this equality exact, we have to take the limit where these delta m mass elements get smaller and smaller. In that limit, the summation becomes an integral and the equality becomes exact. So we write this down as the limit as delta m goes to 0 of the summation. And this whole quantity that multiplies the angular acceleration alpha, this limit of the summation, we give a symbol I to it. And so the moment of inertia I is defined as this limit of the sum of delta m times r squared over all the pieces of the object, and that limit of a sum we write down as an integral. So what this is doing, it's adding up this product for the entire object, and this product is made up of each piece of mass multiplied by the distance of that piece squared away from the axis. So what I now invite you to do is take a look at this new equation that we've written down where the sum of the torques is equal to moment of inertia times alpha, and compare it to our more familiar version of Newton's second law for translational motion. Back in chapters 4 and 5, we showed how the sum of all the forces acting on an object is equal to its mass times its acceleration. Here, we've now got something very similar where we add up all the torques acting on a rotating object, and it's equal to some constant, which is related to the mass of the object, times the angular acceleration, alpha. So look at these two equations. They're so similar that in fact the second equation we call Newton's second law for rotational motion. M in translational motion represents the resistance that an object has to being accelerated. The larger m is, the larger force you have to use to get it to accelerate. I, for rotational motion, measures the resistance of an object to being rotated. If I is large, that means you have to apply a large torque in order to get the object to rotate. Now, what do we do with that I? How do we get values for I? I, we can see if we just go back, I depends on the distribution of the mass around the rotation axis. The more mass you have at larger distances away from the rotation axis, the larger the moment of inertia will be. The more resistant the object will be to getting rotated. But how do we calculate that? Well, we can use calculus to do it. For simple shapes like disks and rings and even rods, linear rods, it's not very difficult to do those kinds of calculations. Of course, they depend on the size and shape of the object, how much mass it has, and where the rotation axis is. But I'm not going to emphasize these kinds of calculations in the course. However, what you should be able to do is use the results of those calculations that are tabulated in your textbook to find the moment of inertia for composite objects about a certain axis. The idea there is if you have a composite object, it's composed of two or more pieces that are stuck together and that are rotating together. The basic idea to find the moment of inertia of a composite object is to find the moment of inertia of each individual piece and then add them up. So in other words, if I have three pieces that make up an object and each of them I can find the moment of inertia for, then for rotation about a particular axis I just add up their individual moments of inertia to get the total moment of inertia of the system. Here's an example. Find the moment of inertia of a cylinder of mass m and radius r, and unless we're told otherwise, we always assume that these kinds of objects have uniformly distributed mass. So the cylinder has its mass distributed evenly all throughout the volume. And to this cylinder, we're going to attach a small ball with radius at the radius of the cylinder, at the surface of the cylinder, with a mass m/3. So we're going to assume the cylinder rotates about an axis that goes through the center and is perpendicular to the plane. So here's our cylinder in cross section, and that has mass capital M and radius r, and we'll attach a small ball that has mass m/3 at the rim, which is going to be a distance r away from the rotation axis. So the total moment of inertia of this system as it rotates will be the moment of inertia of the cylinder about the axis plus the moment of inertia of the ball about the axis. Remember, the axis goes through the center of the cylinder. So we look up the moment of inertia in our textbook for a cylinder for an axis passing through its center, and we find that it's 1/2 m times r squared. And these sorts of simple formulas are very common when we look at simple shapes. So that's the first term. What about the ball? Well, the definition of the moment of inertia is you take the mass of each piece and multiply them by the square of the distance to the rotation axis. And if this ball is small, we can treat it like a point mass, where all of the mass, m/3, is at a distance r away from the center. And so, in fact, the moment of inertia of this ideal ball, if it's very small, will be its mass times r squared, because r represents its distance away from the rotation axis. So these two put together will give us the total moment of inertia of this system. Now, you might object to this. Again, I said something about an ideal ball or a very small ball, and that's true. The assumption that we're making is all of the ball's mass is at a distance r away from the axis. That will be a good approximation if the ball is small. It will not be a good approximation if the ball has a significant size in comparison to the radius of the cylinder. So be aware that we make some approximations here. Now here's an example where we're going to use our new version of Newton's second law for rotational motion to analyze the motion of a relatively familiar system. Imagine that we have a cylinder of radius r, and it's got a string wrapped around it and two masses hanging from the string on either side. When we did these problems before, we treated this cylinder like a pulley that had no mass. And so as a result of that, we were able to assume that the tension in the string on both sides of the pulley was the same. And we did a problem where those two forces were just assumed to be T. In the case of now an object like this cylinder that is not massless, that actually has a mass associated with it, the only way we can get it to rotate is if one of these tensions is larger than the other one. So we actually have to now take that into account. We will still treat the pulley, this rotating cylinder, as if there's no friction as it rotates. However, we can't treat it as if it's massless. So the pulley we'll treat as a uniform circular disc or a uniform cylinder of radius r and mass m, and its moment of inertia will come into play in the analysis of this situation. If the pulley were massless, then T1 and T2 would be the same, and we would find out that the system accelerates with the mass 2m going downward with an acceleration of 1/3 the acceleration of gravity. However, when we do this problem, we now take into account the Newton's second law for each of the two masses in the familiar form, right, where the sum of the forces equals mass times acceleration, and then we'll use Newton's second law to write down the equation appropriate for the rotating cylinder. That will be the sum of the torques will be equal to moment of inertia times alpha. So we'll actually get 3 equations, and we will be able to find the unknown acceleration of this system. And in this problem, rather than work it out now, I'm going to work it out during class. But it's a great example where we have to use Newton's second law in both the linear form and in the rotational form to solve the problem. Now let's go on and just finish up by talking about rotational kinetic energy. Because as an object is rotating about a fixed axis, it's not moving through space. The center of mass is not moving. However, there's still rotational energy associated with the motion of each of the pieces of the object. And their motion is simple. We've already talked about how a rotating object about a fixed axis, each piece on that object traces out a circular path. So let's imagine that we have this oddly shaped object. It's rotating counterclockwise with a rotational velocity or an angular velocity omega. And let's look at this little piece of mass delta m and write down how much kinetic energy it has. And of course, it's moving at a tangential speed v sub I. So delta k sub I, the kinetic energy of this piece, is equal to 1/2 its mass times the speed squared, v sub I squared. That's easy. Okay? And now we're going to make the substitution because v sub I is equal to r sub I times omega. That's the connection between the rotational velocity of the entire object and the linear velocity of one piece of the object. So v equals r omega goes in here, we square it, and we get delta k sub I is 1/2 delta m r sub I squared times omega squared. Why do we do this? Because now when we sum up all of the kinetic energies of the pieces of the object, we write this as a summation, the omega is the same for every piece. So the omega comes outside the summation. And notice what happens when we do this. The total kinetic energy of the whole object, approximately, is 1/2 omega squared times this summation. And that summation should look familiar. In fact, it is the very same moment of inertia that we defined just a few minutes ago. So, when we take the limiting case where those delta m masses get smaller and smaller, then the sum becomes an integral, and the equality for the kinetic energy to be equal to this becomes exact. So we get the result that the rotational kinetic energy, the entire rotational kinetic energy for the whole object, is 1/2 omega squared times this integral, r squared dm, and that's what we called I, the moment of inertia. So we get a very simple formula for the rotational kinetic energy of an object rotating about a fixed axis. So once again, it's all in terms of this moment of inertia, which we can look up in the book for simple shapes. Notice that just as in kinetic energy for a translating object, where the center of mass was moving through space with a speed v, we have something quite similar, and the common features are that there's motion, so the translational kinetic energy involves translational velocity v, rotational kinetic energy involves the rotational velocity omega, and the mass and the moment of inertia play the same role in the two equations. So if I remember the translational kinetic energy formula, 1/2 mv squared, all I have to do is replace m with I, and then replace v with omega, and I get the new equation for the rotational kinetic energy. So m and I play the same role. They both depend on the object itself. V and omega are related. And so these two equations, you should be able to look at those and see that they're actually quite similar. So let's just now summarize what we've talked about so far for rotational quantities and point out where there are these analogies between quantities for linear or translational motion and their corresponding quantities for rotational motion. When we talked about the path of an object along a circular arc, we usually used S to indicate where it was along that arc, and we could also use X if this were truly a one-dimensional motion case. Well, for rotational motion, we use the angle theta to indicate the position of an object. So that's angular position. Translational velocity v is replaced with rotational velocity omega, or angular velocity omega. Translational acceleration a is replaced by rotational acceleration alpha. Mass m in all of the formulas for translational motion gets replaced by the moment of inertia when we write down the corresponding equations for rotational motion. And F, which plays the important role in Newton's second law for translational motion, gets replaced by the torque in rotational motion. Now there's one more quantity that we defined in translational motion, and that was the linear momentum p. And so there turns out there is actually a rotational analog to this, and we'll get to a discussion of that a little bit later. But hopefully this table that shows the relationships between the translational and rotational variables will be helpful as you try to understand the equations for rotational motion, but also as you try to remember them. Because it's very easy, if I remember once again that kinetic energy is 1/2 mv squared, then I replace m with I and v with omega, and that gives me rotational kinetic energy is 1/2 I omega squared. So we'll get good practice doing this as we work through problems in this section of the course. One last thing, I'll just show you an example of a problem that I'll work out in class where we can apply energy conservation to an object in rotational motion. Imagine that we have a thin rod of mass m and length L, and the axis it's pivoted about is an axis through one end. So we have a peg drilled through one end, and perpendicular to the page there's a rotation axis. And we move the rod so it's in this vertical position, and we're going to let go of it. And when we let go of it, it's going to swing down and eventually reach the very bottom. So we want to understand what will characterize its motion when it reaches the very end. So if the rod is positioned vertically and given a tiny little nudge, we want to find its maximum rotational speed, which of course you can figure out without too much trouble. That will happen when the rod is vertical, but it's hanging down from the pivot point. So let's just draw the before and the after sketch. What we would like to know is when this thing now has swung down and is in, for just an instant, is in the vertical position downward, what is its rotational velocity omega? And there's a very straightforward way of applying the law of conservation of energy to this problem, except when we write down kinetic energy, we'll do it in the rotational form. So instead of 1/2 mv squared, we will use 1/2 I omega squared to write down the kinetic energy of the rod. Again, I'll do this in class, but I wanted to mention this as the type of problem that you'll see on the next homework assignment. I'll see you in class.